All right, so the next set of videos are gonna be pretty quick because this is stuff we've been working on all year long. You should be really good at it, but let's just go through it anyways. So what we're gonna talk about is this idea of stoichiometry. Stoichio meaning elements, metry to measure, so we are measuring elements. It all comes back down to this idea of 1 AMU, 1 atomic mass unit. 1 atomic mass unit is the amount of weight that we have given for a single proton. So a single proton weighs 1 AMU. Therefore, we would look at carbon. Carbon with 6 protons. We would say it has 6 AMUs for its atomic number, but we would say that 1 AMU for a proton, it's about 1 AMU, it's 1.0660 or something like that for a neutron. So we would say it has 6 AMUs from the protons, and then on average, it will have 6 AMUs for its neutrons. So we'd say that carbon has a mass number of 12 AMUs. Not really its mass number. We would say its amount of AMUs it has is 12 on average. If you have 6 neutrons and 6 protons, you have 12 AMU. With that being said, we get to Avogadro's number. With Avogadro's number, Avogadro says that 6.02 times 10 to the 23rd is 1 mole. And a mole, just short for the word molecule, a mole is a unit of quantity, like a dozen is 12. I'm going through this pretty quick. And so what we have is 12 AMU. If I have 6.02 times 10 to the 23rd AMUs, so I have a mole of carbons, means I have a mole of the carbon stuff. So it'll be 12 times 6.02 times 23 AMUs. We would say that that weighs, if I have 1 mole of it, it is going to weigh 12 grams. Now, pretty much we'll never use AMUs ever again. Ever again. It's just the idea that a mole of atomic mass units is equal to 1 gram. That's it. Now, with that being said, when we look over at the periodic table here, all of these mass numbers are the weight of these atoms in moles. So if I have a mole of lead, we would say on average it weighs 207.2 grams. We go up there, carbon, there's my carbon of 12, my nitrogen of 14, my oxygen of 15.999. Now, with that being said, if protons weigh 1 AMU and neutrons weigh 1 AMU, then how are we getting numbers like 207.2? How are we getting numbers like 12.01? How are we getting numbers for phosphorus, 30.9738? And that is because for atoms, we have isotopes. And what that means is, in order to be carbon, you must always have 6 protons. 6 protons means you have carbon, plain and simple. But there are isotopes of carbon, which means sometimes you'll have a carbon, this is all carbon, with 6 protons and 6 neutrons, thus a weight of 12. You might have yourself a carbon that has 6 protons and 7 neutrons with a weight of a 13. So let's just take those two real quick. This is an isotope of this, and this is an isotope of this. Basically, they're both carbon, but they have differing numbers of neutrons. Now, with that being said, if this one right here, let's say, makes up 95% of all carbons you would find, 95% of all carbons you find out in the world will have a mass of 12. I would take my 12 and multiply it by 0.95, and I'm gonna get a number. I'm gonna get some number a little bit less than 12. If therefore 13, and this was 5% of all of the carbon out there was found as 13, I would take my 13, multiply by 0.05, and I'm gonna get a number. I'm gonna get a number, and I'm gonna add those numbers up, and voila, I get the average atomic mass of all the carbons that are out there. Now, there might be more isotopes, so we'd have to find percent by abundance of those things as well. So what that does is it explains to you, when you look at this, it explains to you why these numbers up here have differing numbers that aren't just whole numbers there. And so if I told you, for instance, that let's say gold, now let's do an easier one. Let's go ahead and go beryllium. If you look, beryllium has a average atomic mass of 9. So if I told you there were only 2 isotopes of beryllium, and one of them was 4 protons and 4 neutrons, and one was 4 protons and 10 neutrons, well, then you can start looking at the average and go, oh, maybe it's like a 50-50. Maybe it's like a 50-50, because you can see that majority of beryllium is right around 9. And so if you have yourself 10 and 8, the average would be 9, 50-50. But let's say if I told you that beryllium, or we can go to lithium, that lithium had only 2 isotopes. And one of them was 3 and 3, 3 protons, 3 neutrons. And the other one was 3 and 4. You would assume that the majority of lithium that's found out there in the real world would be the 3 and 4. Why? Because the average is around 6.941. That's if there's only 2 isotopes there.